What if our computers could think like the human brain, not just follow instructions, but learn, adapt, and evolve like neurons firing in our minds? And what if, instead of electrons moving through silicon, these thoughts were powered by light itself, fast, efficient, and almost instantaneous? Welcome to the future of intelligence, neuromorphic and photonic computing, where physics, biology, and artificial intelligence merge to redefine what computation means. You're watching The Learning Studio, and in today's episode from our physics playlist, we'll explore how the next generation of computing will be built not just on transistors and code, but on neurons and photons. You can watch the entire physics playlist by clicking the link below in the video description. This episode is part of our section Physics Meets AI, the computational frontier, where the boundaries between matter, energy, and intelligence begin to disappear. The problem: why we need a new kind of computer. Our world is producing data faster than traditional computers can handle. Every scientific simulation, AI model, and quantum experiment generates petabytes of information, yet our silicon-based chips are reaching their physical limits. Even the most powerful supercomputers are struggling to process AI workloads efficiently, consuming enormous amounts of energy and producing heat that's hard to manage. Nature, however, solved this problem billions of years ago, in the human brain. Your brain performs roughly 10 superscript 16 operations per second, yet it runs on the power equivalent of a small light bulb. How? Through neuromorphic computation, a form of massively parallel, event-driven processing where billions of neurons communicate using sparse electrical pulses called spikes. That's the inspiration behind neuromorphic computing, computers that don't just process information, but think in the same physical way our brains do. Neuromorphic computing, the brain inside the machine. Neuromorphic computing uses hardware designed to mimic the neural architecture of biological brains. Instead of transistors switching binary states, these systems use artificial neurons and synapses that transmit electrical signals like real nerve cells. These networks can learn, adapt, and self-organize, not through explicit programming, but through experience, much like our own neural pathways strengthen and weaken with time. Some of the leading neuromorphic chips today include IBM's True North, which contains over 1 million programmable neurons. Intel's Loihi, capable of on-chip learning and real-time adaptation. Spinnaker, a supercomputer inspired by biological neural networks. These chips are not just faster, they're energy efficient, scalable, and inherently parallel, making them ideal for AI, robotics, and even space exploration where power efficiency is critical. Neuromorphic systems could one day give rise to thinking machines that perceive and reason more like humans, blending physics, biology, and computation into one seamless framework. Photonic computing, when light becomes logic. Now, imagine if we could take that brain-inspired structure and power it with light. That's the vision of photonic computing, where information is processed using photons, particles of light, instead of electrons. Photons travel at light speed and don't generate heat the way electrical currents do. By using optical components like waveguides, lasers, and microresonators, photonic computers perform calculations using the interference and superposition of light waves, directly applying the principles of quantum and optical physics. These systems can execute trillions of operations per second while consuming a fraction of the energy used by conventional chips. What's more, AI models built on photonic hardware can perform matrix operations, the heart of deep learning, almost instantaneously. This makes them ideal for powering data centers, edge devices, and even AI-driven telescopes or fusion reactors, where speed and precision are critical. Neuromorphic plus photonic, the perfect fusion. Now combine both worlds, the brain-like adaptability of neuromorphic systems with the light-speed efficiency of photonics, and you get a new paradigm. Neuromorphic photonic computing. Here, light pulses act as spikes in a neural network, propagating through optical pathways that mimic synaptic behavior. This approach could revolutionize AI by enabling real-time, energy-efficient learning systems, capable of processing complex data streams directly from sensors. Imagine autonomous robots that think at the speed of light, AI systems that respond instantly without cloud processing, or scientific simulations that unfold as fast as nature itself. This is not theoretical. Early prototypes already exist, and research in optical neural networks and silicon photonics is accelerating rapidly. Applications, from space to subatomic scales. Neuromorphic and photonic computing are reshaping how we approach science and technology. Fusion energy, real-time plasma control using ultrafast neural feedback systems. Astronomy, optical neural networks analyzing terabytes of cosmic data instantly. Robotics, autonomous machines capable of low power, high-speed decision-making. Healthcare, AI-powered sensors detecting biological signals in real time. Quantum computing, hybrid systems where light, matter, and AI converge for scalable computation. These aren't just incremental improvements, they're steps toward a new computing era where hardware is as intelligent and adaptive as the algorithms it runs. The future, the rise of physical intelligence. The next decade will mark the dawn of physical intelligence, where computation, energy, and matter work together. Neuromorphic and photonic computers won't just imitate the brain, they'll extend its capabilities, bridging the gap between human thought and machine logic. They'll enable AI-driven physics, where simulations, experiments, and data analysis happen in real time, helping us design new materials, explore other planets, and even decode the origins of consciousness itself. This is the future of computing, a symphony of light and neurons, guided by the laws of physics and powered by the spark of intelligence. Why it matters. The evolution of computing has always been tied to physics, from the discovery of electrons to the manipulation of quantum bits. But now, we're entering an age where the hardware itself becomes intelligent, built not just by engineers, but inspired by the very mechanisms of life and light. For students, this field represents the future, where physics, AI, and neuroscience merge into one frontier. For researchers, it's a gateway to building systems that think and learn at physical limits. And for all of us, it's a glimpse of what happens when human curiosity meets the computational power of nature itself. This is the Learning Studio, and this was our episode on neuromorphic and photonic computing, where light and intelligence converge. If you enjoyed exploring how physics is reshaping the future of computing, don't forget to like, subscribe, and check out our physics playlist linked below. In our next episode, we'll dive into AI-augmented scientific discovery, how machines are not just solving equations but uncovering new laws of physics. Because the future of intelligence won't be coded, it will be illuminated.